There we go. All right. I forgot about the light too. Got to have the right lighting. All right. So I'm checking everything right now. They seem to be okay, and I'm looking at Discord, and my voice should be synchronized with the image now. So far, so good. And I'm going to start screen sharing because that's going to be the last thing that can potentially break the whole thing. So we'll give it a try now. All right. All right, so now we got everything going. I got the YouTube stream, I got screen sharing on Discord, I got my voice going, and I think everything is still relatively synchronized. I'm not dropping any frames on YouTube's side. I did have to change the frame rate on YouTube, so for those of you who want to rewatch YouTube, you will find that the frame rate of YouTube is only about 5 frames per second instead of the Discord 15 frames per second. But I can only type so fast, and I can only move my mouth so fast. So I don't think it's going to cause any actual issue. It's just that when you look at my expression, it's going to look a little choppy on YouTube's side. All right, so does anyone notice any problem with the Discord streaming? It's still out of sync. Okay. Because I'm monitoring my own voice, because when I talk, there's a little green halo around. It's choppy. Huh. Okay, I cannot tell whether it's choppy or not on this side. Oh, audio is good. Okay. Okay, so I guess it's just the screen itself, being choppy. Okay, wait, hold on a second. Let me check on one more thing. And let's see. Okay, so because earlier we have a networking issue. Um, one of the computers was doing a Windows update, so it was saturating the pipe, so to speak, and that's potentially why it was a little choppy. It should not be networking issues now. So if it is choppy now, it is just because my computer is too slow. Because I tried everything and it's not it boils down to I just don't have enough processing power to do all the encoding. All right, so without any further issues, related to streaming, I'm gonna continue with the lab that I did yesterday, which is the subroutine that we called and then returned. So that's what we'll do next. So first thing first, I'm gonna have to go back to that window, and I may not have the content anymore because I rebooted the computer today while I was working on those issues. So that's right. Okay, so I did I did lost. I lose. Okay, grammar. I lost the files that I worked on yesterday, but that's okay because now I can just work on those again, and you can use this as an opportunity to kind of get refamiliarized with the concepts that we talked about yesterday. So it's going to go a little bit faster than yesterday because the bulk of the content was already discussed yesterday. So it was about calling a subroutine. So I'll give you a C version, and then I'll give you a TTP ASM version, and those two will be side by side. So on the left hand side, we're going to have the C code. So the C code is going to be pretty simple. We have a function f that is not going to do anything, and then in main, we'll call it twice like that, and then return 0. So that's our C code. Doesn't do a single thing, but it does call the subroutine twice, and if we track down the execution, we should see it, going from the first call to the subroutine, going back to the second call, and then call again into the subroutine, and then back to the return statement in main. So in the assembly code, we are going to, oh, okay, some stats is covering the bottom half. Oh, okay. So I just have to, sorry about that. Okay, I have to undock that. Let me see, is that gonna do it? That ought to do it. There we go. All right. All right, so getting back to the assembly code. So if you want to use the trace analyzer, which I think is pretty much what you have to do if you want to debug your program, that's kind of what you have to do. So you have to start with a no op instruction. That has to do with a bug in Logisim. But it's an easy fix. You just have to waste 1 byte for a no op instruction. And then if I remember correctly, yesterday we also initialized the stack pointer at this point, and then we do a JMPI to main. So the only reason why I need a JMPI to main has to do with I want to preserve the order of the definition of F and the definition of main. So now we have F defined here right after the JMPI instruction, and the main defined all the way down here. Now main being main, it doesn't really have a place to return to, unlike in the C code. The C code has a place to return to because libc, or the C library, actually has a call to main that is not visible to you as the developer. So it does have a place to return to clean up, after main. But in assembly code, there's no such thing because main is the only code that we start with. So we just have a halt instruction here. Now the alternative is not to even define main, and we basically just use this portion of the code instead of a JMPI to main. We just put main over here. That is okay as well. But I'm not going to do it in this class because I want you guys to visibly see what main becomes when we have main in the C code. So that's why I'm not going to hide the main function, because I want that to be more visible. And then when main, the first thing we want to do is to call F, and to call F we have to set up a label so that we can remember where we want the subroutine to return to. So I can't remember exactly the name of the label that I used yesterday, so I'm just gonna create a new label name now. I'm just thinking about how to call the label name. Okay, we can make this long. Okay, we can say first call to F returns here. Okay, how about that for self-documenting labels? So this label is indicating where the first call is going to return to. But yesterday we spent quite a bit of time to talk about the stack, and okay, I'm just looking at the text channel. Okay, good. So we need to push the address corresponding to this label on the stack, because the stack is the only thing that the caller and the subroutine being called can use for quote-unquote communication. In this case, what we need to communicate is where should the subroutine return to. So we want to push first call to F returns here. Okay, so we're pushing that label, but unfortunately in TTP ASM there's no such opcode for pushing a immediate value, and it is by design. Okay, by design I did not want to implement that specific instruction because I want you guys to see what is actually behind that instruction. So instead of doing that, we have to first load the label into a register. So we're just going to put this label into register A, and then we have to perform the push operation, which starts with a decrement D to reserve a byte on the stack, and then we do stda, so that we store the value of register A or whatever value register A has to the location in memory that register D is pointing to. So this is what we talked about yesterday. This is the push operation. So after we push the return address, then we can continue execution in F, which is really the job of a simple JMPI instruction. So now we want to shift our attention to the subroutine. The subroutine is empty. There's nothing to do, but it still has one little thing that it has to do, which is to return to the caller. So how it returns to the caller is dependent on the agreement between the caller and the callee. So the agreement is when a subroutine gets control, the stack pointer always points to a location in RAM that stores the return address. In other words, where a subroutine is supposed to return to is stored in the byte, in this case, that the stack pointer points to. And that is always the case. So F is a subroutine is going to make use of that agreement. So the first thing it's going to do is to do an LD instruction. So it's going to do LD, and in this case, we can use registers A, B, or C as the register receiving the value. So I'm just going to randomly pick C over here. Okay, so we are just retrieving the byte that the stack pointer is pointing to so that we can use it later on. But once the byte is retrieved, that byte doesn't need to be on the stack anymore. That location on the stack can now be used for other things. So we want to deallocate that byte on the stack, and that is done by incrementing the stack pointer. This was also something that we talked about yesterday, so I'm not going to go into the details of why increment D is deallocating and why decrement D is allocating. And at this point, we have popped the item from the stack, and as a result, we are ready to continue execution at the location that register C is pointing to. So using the usual instructions, this would be something that we think would be the instruction to use, but it's not going to work because JMPI requires an immediate value as the expression on the right hand side of JMPI, the opcode. And C is not causing a syntax error because C can actually be a label. In other words, there's no confusion whatsoever if you decide to use the name of a register as a label because they cannot be in the same context, and as a result there's no conflict. And that's why the syntax checker is not able to check and go like, hey, this is a problem, because it really is not a problem. Now if you use any name other than A, B, C, or D, it will still not be a problem because you can always define a single letter label. But the proper instruction to use is JMP, and we want the JMP C. So in this case, the JMP instruction is going to where the register is pointing to. In this case, where register C is pointing to. So that's the main difference between JMPI and JMP. Alright, so we are done with the first call. Okay, so here is an advice, when you want to write your code, because there will be programming assignments, from this point on, and those are not going to be trivial homework assignments. And because of the compressed schedule, you are not going to have a whole lot of time to write your code. So you have to learn how to write your code so it is easier to debug, and you have to learn debugging techniques so that if you do make a bug, it's easier to find a bug and fix it. So at this point, I'm going to stop because even though I do have a second call in the C code, I want to make sure that the first call is working out first. So I'm going to quit at this point. And this is just me copying to the clipboard so I can actually paste it into the assembler. So how you do this is probably something a lot easier because most likely you're using Windows or Mac OS, and you have a GUI type of editor that makes it a little bit easier to do. But in my case, it is this is a command line editor, so it's not going to be as intuitive. Alright, so we are now back to the assembler. Remember the problem that I had yesterday of the trace analyzer? I figured out the problem, and I will show you the answer to that particular problem. All right, so I'm gonna erase column A of source just to make sure that we don't have any leftover code from the previous program. And then we paste the code in. Doesn't seem to have any problems. And then we go to RAM file, and we confirm that A1 is saying v2.0 raw. So we have just confirmed that the program assembled just fine. So at this point, I am going to download this code as a CSV onto my PC. And I'm going to call this call.csv. So every single file related to this project is call.something. So now I can go back to Logisim and run it. Now, when I run the program, okay, let me go back to a command prompt. So when I run the program, I could do it the usual way, which is basically just do it using the GUI mode. The problem with the GUI mode is you cannot really track down how your program executed. So if it didn't execute correctly, the GUI version of Logisim is not going to be able to help you much. So I'm going to start introducing how to do all of this using the command line. This is something that we did in the first week. And I said, you guys probably want to learn how to do this. I'm hoping most of you did learn how to do this using whatever operating system that you're using and still remember some of it. Alright, so it's java-jar, and then you have to supply the path to the jar file. In my case, it is in tilde slash documents slash CISP310 slash logisim.310.jar. So after you specify the jar file, if I press the enter key right now, it's going to start Logisim in GUI mode. The usual, there's no circuit loaded. It's just Logisim with a blank circuit. That's what it's going to do at this point. But I want to specify that I want to run the processor. So now I have to supply the path to the processor circuit file itself. And in my case, this is the path to processor 0004.circ. In order for all the tools to work properly, you have to use processor 0004 because processor 0003 is not going to have some of the output pins to make the trace analyzer work correctly. So you have to use 0004 from here on. Alright, so if I press the enter key right now, Logisim is going to start up in GUI mode. It's going to have the processor loaded, but then I still have to go to the RAM component, right click, load the CSV file, and then I have to use Control T or Control K to start the clock ticking. Okay, either single ticking it or I can use auto tick. Either way, it's not going to leave behind a useful trace for me to debug the program if I make a mistake somewhere else. So that's why we have to use more commands now. Okay, so we're going to use a dash load, and then we supply the CSV file name, which is call.csv. So what this does is it will locate the only RAM component in the circuit, and it would load the content of the CSV file into that RAM component. Obviously, this is not going to work if you have multiple RAM component in the circuit, but since processor 0004 only has one single RAM component, it'll be fine. Okay, it will find that RAM component and then load the content of the CSV file, which consists of all the opcodes of this program, into that RAM component. So if I were to press the enter key now, it's still going to start up in GUI mode, except this time the processor will have the RAM populated with the content of call.csv, which is also not what we want to do, because we want to run this without getting into the GUI mode. So to do that, we have to do a dash tty. TTY stands for teletype, which is the name of the very, very dumb terminals used in the I would guess about 70s. They look like typewriters, but they're actually terminals. And then we specify table so that the output is going to be in a table. It's going to be a tab separated table format. Whew. Okay, so yes, it's kind of long, but we are almost there. So if we are to press the enter key right now, the output or the trace is going to appear on the in the command line interface. So let me just do that so you can see what it looks like. So I'm pressing the enter key right now, and this is the output. In other words, it is just sending the output directly to the um, command line interface, and it is just a whole bunch of zeros and ones, which is not going to be very useful for us. So I'm going to repeat the command, which is just using the up arrow key. I think most command line interface would do this. If you press the up arrow key, it's going to repeat the previous command. So now we want to use the redirection symbol, which is the greater than symbol, so that all the output is going to be captured in a file that I'm going to name here. That file is going to be called .tsv. Okay, so you have to be careful not to reuse the same name. So CSV, I would use that for the opcode file, so that Logisim can run the program. And then TSV, which is tab separated value, is going to be the extension of the log. Okay, this is equivalent to the log of the JXI lab. Okay, but except this is far more complex than the other one. So we capture that just like that. Okay, so TSV, the call.tsv file is really a text file. So if you want to, you can use Notepad or whatever favorite editor you have to look at the content. But once again, it is not going to be very helpful because it's just a whole bunch of zeros and ones. So we are not going to use a text editor to look at it. You could use a spreadsheet to open it. Okay, a spreadsheet will not have a problem opening it, except it will still just be displayed as a whole bunch of zeros and ones. So what are we going to do with the TSV, right? This was where I made a mistake yesterday because I was using a trace analyzer spreadsheet and it didn't work. Well, I forgot that I integrated the trace analyzer into the assembler spreadsheet. So now they're all in one single spreadsheet. I completely forgot about that. And that's why it didn't work. So what I need to do now, okay, is to copy and paste the entire TSV in. Oh, wait, no, I take it back. So let me go back to the assembler, because the assembler also contains the trace analyzer. And I need to find out which tab contains it. Oh, we are on it already. All right, so if you look at all the tabs of the assembler, and you have to kind of use the arrow key so that you can see, you can scroll the labs to the tabs to the right. So if you do that, you will see that there's a tab called Trace Raw Data. So go to that tab. Okay, click on that tab, and we are going to have to do an import over here. So this part is something that I did yesterday already, but it doesn't hurt to repeat it. So if you want to time mark in the video in today's lecture recording, now would be a good time to do it. Okay, so right now the time is 5:51. So just jot down somewhere, and say that at time 5:51, TAC demonstrated how to use the trace analyzer feature. All right, cool. Thank you, Eric. That's really useful using the text channel. All right, so now we go to File. Now, if you have done this a few times, it's not going to be super duper difficult, but the first time you do it, the first few times you do it, it's going to be cumbersome. But it's no more than just your following instructions. So you go to File, make sure that the current tab is Trace Raw Data first step. Second step, go to File, go to Import, and then click on Upload, and then click on Select a file from your device, and then click on, now this one you have to be careful too, because there are two files. Now that's just my naming convention, because I named one CSV, the other one TSV. Make sure you click on the one that has the extension of TSV for tab separated value, and then click Open. And now we have to specify the options for importing. We want to select Replace Current Sheet. Okay, so that's important. Then we want to specify using tab as a separator. And we also want to uncheck convert text to numbers, dates, and formulas. So this is really important, and I'm going to do you guys a favor and do a screenshot and post it into the text channel. Whoa, there we go. Alright, so we want to copy to the clipboard, and now I can paste it into the text channel. There you go. In other words, I don't want to hear anyone asking me, so what option should I use when I import the TSV today? Yeah. So click import. I think it's working already. It's just my computer is really slow right now. And yep, it's just really slow right now. Hopefully I'm not dropping frames. Okay, so I'm still not dropping any frames, and I think this one is done at this point. So when trace raw data is done being analyzed, you want to go to analysis, and analysis is going to give you a much cleaner, even though it's still kind of long, kind of lengthy, but it's a lot cleaner. So let me explain what you're seeing in the analysis tab. In the analysis tab, you have five columns. Column A is indicating the addresses at which opcodes were fetched and executed. So this cell specifically is saying location 00 or whatever opcode at location 00 is fetched and executed. This one says, the opcode at location 01 is fetched and executed. This one says the opcode at location 03 is fetched and executed. We skip 1 byte here because the LDI instruction takes 2 bytes. Okay, so location 01 and location 02 both belong to the LDI instruction. So that's why sometimes you would see a byte being skipped. And then column B is will report back if a RAM location is read. Sometimes it is not essential. Sometimes it really is not important. What byte it has read. Other times it is. Column C, it will tell you what location is being changed in RAM, and in this case we are not changing anything in RAM until much later, so that's why you see it being blank all the way up to here. Column D will reflect any register changes, so we can see how the instruction at location 01 is changing the register D to 00. So that is really useful because now we can actually correlate the log, and using the program counter, when an instruction is fetched and executed. So we can now go back to the assemble tab. Okay, so assemble tab is right here. So now we can go back to the assemble tab and look at column W. Column W is are the addresses in RAM in hexadecimal. So whatever you see in column W corresponds to in the analysis column A. Except in the analysis tab, you are looking at the trace left behind when the program executes. So do we have any questions about what the trace analyzer has or what the analysis tab has? I'm looking at the text channel and I'm not seeing anything. Okay, all right. So let me just kind of go ahead and do it step by step, right? This is the no op. This is the LDI instruction resulting in register D being initialized to 0. This is the JMPI instruction resulting in the next location to execute code being 08. So if I were to go back to the assemble tab, I should find location 08 corresponding to main. So right here, we look at the definition of main, and indeed it is at location 08. So this is why it is really kind of helpful to have the trace analyzer, because it actually logs everything as your program executes. So this is in main, and in main the first thing we did was to do a LDI so that we are loading the return address of the first call to F into register A. And that's why register A is now initialized with 0E. And once again, if you were to go back to the assemble tab, you will see the long name that we defined for that label is indeed at location 0E. Okay, so once we load that value, the return address, into register A, we're supposed to push it on the stack. So when we go to the analysis tab, the next instruction is decrementing the stack pointer. The stack pointer was 00 before. When we decrement it, it becomes FF. So, and then the next instruction is the ST instruction. So this is why you see column C having an entry, because when we execute the store instruction, the ST instruction, we are copying something from a register, in this case register A, to where register D is pointing to. Register D has a value of FF, so that's why you see at location FF, the content is now updated to 0E. There's also a reason why the asterisk symbol is used here, because it is the dereference symbol in C++. All right, so moving on. The next instruction is a JMP instruction. So this one is for this is a JMP I to F. And that's why the next instruction is not in sequence anymore. Because normally, if you have a instruction, the next instruction is going to be right after that. But you can see how we jumped from 0C, which is where the JMP I instruction is located, to 0E, to 05. 05 is the label of F. Once again, we can kind of switch between the labels. So we can go back to the assemble tab and look up the label F, and label F is indeed corresponding to location 05. So if you think all this left, right, scrolling left and right of the tab is silly, okay, because we have to do this a lot. You can actually move the tabs. Okay, so once you make a copy of the spreadsheet, or you can make a spreadsheet after I kind of move these things around a little bit. So I can actually move analysis to the left hand side and make it to be right next to assemble. So now we have the source, the RAM file, assemble, and analysis right next to each other. The other ones you don't need nearly as much, as often. So we can move the trace raw data to maybe here. So that's where everything else that we don't need to access is out of the way. So I think this is a better way to organize it. You can always move the tabs any way you want. Okay, so there's no limitation of how you can arrange the items. All right, so getting back to the code. This is the entry point of the subroutine, which is F colon. And the first thing we do over there is to do a LD instruction. So the LD instruction is to copy the content at the location that the stack pointer is pointing to. The stack pointer is pointing to location FF, and we're going to copy the byte at that location to register C. And that's why you see location FF is being read in this case, and the content at that location, which is 0E, is also copied to register C. Can we also see the code on the side? Okay, so if you want to see the code on the side, we can, let me see. All right, so you mean the TTP ASM code, right? Oh, we want to quit this. And I don't know why it complains about that, because it's still in an editor in the other tab. There we go. All right, so this is my editor. it's not as easy to shift between these two. So if you want to look at the code, or if you want to look at multiple tabs at the same time, there's one really easy trick. So what you do is you copy the URL at this point. So just do a Control C. Pretty sure there's a way to duplicate it too. So if you right click on the browser tab, you can say duplicate tab, like so. So now we have two windows to open exactly the same Google Sheet, which is not a problem. Okay, this is one of the great things about Google Sheet is you can open up multiple tabs at the same time, but you can only look at one tab at a time. So I'm going to move the tab off screen so it becomes its own window, and then we put it back into the area where things are being captured. So now we can use one to look at not the source but the assemble tab, and then the other one to look at the trace. So you can, on your own computer, do stuff like this so that you can have one to look at the assemble tab, which shows you the code and also the actual opcode and also the locations on one side, and then the other one will show the actual runtime behavior of that code. So I'm not sure whether I'm answering the question from Fulin. Oh, okay, great. Yeah, so it takes a little bit of positioning of your browser windows. Depending on your operating system, you may be able to do something like this. Okay, you can't really see this. I'm going to drag the screen a little bit below so that it's being recorded. So in my environment, I can actually specify a particular window to be always on top. This is really helpful because I can now do whatever I want in the window that is behind it. Like I can just kind of click at different places over here, and you can see how the window in the back does not get brought to the forefront because I have selected that option in one of the window. But this may not be available for other GUI environments, so I'm not really sure whether it's going to be helpful to you or not. So if I need to turn it off, I'm going to have to say same as other windows, I think. So that will cancel what I specified a little bit earlier. So it's not always on top of the other window. So now if I click on a different window, the other window becomes on top. So it's up to you guys. Okay, I know you guys know the GUI environment a lot better than I do, so you can kind of exercise your expertise in this case to kind of display the right content, so it's easier to look at the code and look at the trace at the same time and correlate, between those two. All right, so I'm not quite done yet, so let me go back to analysis because there are a few more things that I need to demonstrate. So this is where we retrieved the return address from the stack, which is on memory, based on the stack pointer, which is register D, and the return address is placed into register C. And then the next instruction is the JMP instruction. Remember, this is JMP, not JMPI, because we are using a register, in this case register C, to tell us where to continue execution. Register C says, let's go ahead and go to location 0E, and as a result, we should end up at location. Oh, wait, okay, never mind, I misspoke. The next instruction is to deallocate that space on the stack. So it is a increment D instruction. So increment D is at location 06, and as a result, register D is incremented from FF back to 00. The next instruction at location 07 is the JMP C instruction. So that's why we are not continuing on location 08 or 09. Instead, we are going to location 0E because register C has the content of 0E, and JMP C is using the content or the value of register C to tell the processor where to continue execution. 0E there's nothing after 0E because 0E is the halt instruction. So when we get to the halt instruction, everything just stops. So we are basically done with this program. All right, so that's one exercise of how to use the tool that is available. I wrote a script to automate some of this stuff. And it is written in bash script. So that means people who use Linux, people who use Mac OS 10, may find it pretty easy to port the script. If you use Windows, you might need to use. Remember, early on in this semester, I told you guys to install Linux. Is it Linux for Windows? But basically, it's a very lightweight virtual machine, so it can actually run Linux alongside with Windows. That will make this process easier. Now, it's not required. It just streamlines certain things, so it's easier. But it's not required because you just saw how I did everything by hand. WSL, thank you, Paul. The Windows subsystem for Linux. Okay, cool. And it's version 2, okay, because WSL1 works differently compared to WSL2. So make sure you're getting WSL2. All right, cool. All right, so now we go back to the editor because we are not quite done with this program. We just got one call. We have to do the other call too. So the other call is going to be about the same as the first one. If I were to turn on the line numbers, I just need to copy and paste, excluding the line of comment, which is on line 12. I just have to copy line 13 to line 17 and then change a few things to make it work. Okay, so we'll use line 13 to line 17, and we'll copy that to line 18. Oh, okay. Should have used line 17, but that's okay. All right. So this is where you kind of have to be careful, because if you use copy, paste, and modify, and you forget to modify one of the things you're supposed to, then your program may compile just fine, may assemble just fine, but it's not going to do the right thing. So we have to change two things, because first of all, we have to change the label, because this label definition is technically now the second call to F return here. Okay, so we have to change the name from first call to second call. But if you get distracted at this point and then later on forget to change the rest of the program, line 18 is perfectly okay in terms of the label being defined and in terms of syntax. Except at runtime, it's going to cause a problem because it will make the second call, which is happening here, when the subroutine is done, it's going to be returning back to here. So you basically end up with a loop that is not going to exit. So we have to change this one to second call to F returns here. Then everything is going to be good. Okay, so we'll go ahead and quickly go through this run and make sure that we end up at the halt instruction, and at that time the stack pointer should be quote unquote balanced. Now when I say the stack pointer is balanced, it means it is going back to its original value of 0 because it was initialized to 0. So we'll go ahead and test this program out. Okay, so I'm gonna do it the Linux way, put it into the clipboard, and then go to source, erase the entire column A, paste again, and then go to RAM file to download the file. Okay, so go to file, and then we download the CSV, and I'm going to give it the same name. So I'm going to call this your call.csv. It will tell me that it's already here. I want to replace it. Go to the command line, switch back to the tab where I ran the commands, and just use up arrow to repeat the previous command to run the program through the command line interface. Press the enter key. It's all done. Go back to the trace raw data tab and go to file, import, and click upload. Select the file, which is call.tsv. Click open, and then change the options. Right, replace current sheet, and make sure that the separator type is tab. Uncheck that, and then do the import data. And it's being done. My computer is kind of slow, so. And the other tab is, I think it's updated already, so we'll give it a try. If you want to find out how long the analysis is, you can actually go to, I don't think it's summary, I think it's, oh, it is summary. Okay, so you can go to summary. It tells us that the trace is 105 lines long. So now you can go back to the analysis tab and just go straight to row 105. There's a way to do it. I think you can click on this icon here, and then you can just say, A105. So that way it will go straight to the cell A105, which is the last tab, and we ended up at location 14. The stack pointer has a value of 00. Okay, you can see how my touch point on the keyboard is not behaving. It's having a drift. Okay, now it fixes itself. But the point is, we have register D, which is the stack pointer, quote unquote balanced, because it is now back to 0. And location 14 corresponds to the halt instruction, because when we go back to the assemble tab, we can see the halt instruction is indeed at location 14. So the point is, the program worked. Okay, we called F twice. The first time it returned to the second call. The second time it returned to the halt instruction. So the program worked the way it's supposed to. And I think it is probably not a bad idea for you guys to basically use exactly the same program and trace through, just go through this exercise and be able to explain what each location in column A is doing, how it corresponds to the source code, and what it actually is doing when that instruction executes. So use your own words to comment this particular table. I think that's going to be a useful exercise. And to make it so that you can make your own file to do this, one way to do it is when the analysis is the tab being selected, you can actually go to File and go to Download, and this time you can use any one of these formats. If you have Excel already installed in on your computer, just export it to or download it as Excel, and then you can use the other cells to write your own comment. In other words, you are taking a snapshot of the trace and use the spreadsheet as a documentation tool so that you can actually describe the runtime behavior of this program and explain what each instruction is doing, why it is important, and so on. So this is one way for you to take notes in a very systematic way. All right, we got one question coming in the text channel, so I'm going to wait a little bit. Yeah, there's a little bit of noise in my background, so I do apologize for that. All right. I can make the TSV file from logging option in Logisim instead of using the CMD. The answer is yes, but it's going to be excruciating painful to do it that way, because you have to capture all the output pins in a specific order, and that's going to be much more painful than doing what I just did. So I would still think using WSL is one option, but the way I do it right now does not even need to use WSL, because it really is just a matter of downloading a file, uploading a file, selecting some options, and the only part that is a little bit more difficult is to run the command on the command line like this, which I don't think is going to be a big issue, because what you need to do is to find out how to specify a path to a specific file. But that's something that we have done already at the beginning of this summer session. So, I mean, yes, it is tedious, but it's not like so tedious that to go for the other option, because the other option is far more painful. And if you make one little mistake, if you order the output pins just wrong, a little bit, it's not going to work. And I just think that's going to be a lot more painful. But don't let me stop you. Oh yeah. Okay. So the bash script, you guys would go like, I want that because it's so easy to use. So the bash script requires a little bit of customization. Um, so I probably want to use off class time to describe it, okay? Because it does involve, it's a little bit more involving. I have one person texting me. Let me see. Oh, okay. So that's a separate issue. I'll address that later. Okay, to the person who just direct message me. All right. So back to bash script. That's right. Okay. So let me switch to the bash script and describe. Show you how cool it is. Okay. So let me go to that folder. If I remember correctly, it's under CISP310 River Spider. There we go. Yeah, I know, it's a funny name for that. All right, so the bash script is called submit. Okay, so let me show you what submit can do. And just so that we know that the script is working and it's not just me doing some voodoo stuff to make you believe that it works. Okay, so we'll erase column A in the spreadsheet right now. So there's no program here. And I just have to specify where the TTPASM is in this case. So it's in my temp folder called .ttpasm, and I think it works. Okay, so I'm keeping my fingers crossed. Yes, so this is fingers crossed and live long and prosper combined. All right, so give it a try. You can see how it's involved in invoking the assembler, downloading the codebag, run the simulator, collect the trace data, and then upload the trace data into the analysis, into the trace raw data tab, and then the analysis tab should have it analyzed. Okay, so I claim that this is auto magical, and let's see whether that worked. So we got the source code here. And then we go to the analysis tab. Oh no. Oh, it does work. Yes, so it does work, and it's just a compacted format compared to last time, because my script has two parts. Okay, one part is on the PC side, and then the other part is on Google side. And the one on Google side does some compacting. It looks cleaner. Okay, that's all. Okay, it still has exactly the same content. It just looks cleaner compared to the previous one. So there you go. I mean, so if you use a script like this, all you have to do is to invoke the script and give it the name of the TTP-ASM file, and it will do the rest for you. So now I think everybody's going like, I want to have that script. I want to run this script. So the problem with is, to run this script, there are a few steps that you have to do. Okay, one is it only works in Bash. If you can get Bash working in Windows, however you get it working is up to you. Okay, I would say WSL is the easiest way to do it, but if you find some other way, like using Cygwin, I'm not sure whether Cygwin Bash will work in this case, but if it does work, hey, it's good. So that's the first hurdle. The second hurdle is there's a passcode, because I don't want you guys to be using my assembler and mess up the stuff that I have here. So there's a little password protection here, and I'm not going to give that password to you. So when you make a copy of this assembler, if you look into tools, let me see, is it in tools? Yeah, so if you look into tools and script editor, there's a MD5 hash included in here somewhere, right here. So this is the simple auth, and it basically the constant here is a hash, is the result of applying a hash function, and the original string to generate this hash is a secret that I'm keeping, that I'm not going to give you. So when you want your assembler to be able to do this, so they can use your own bash script to do the same thing, you're going to have to regenerate that particular hash string, which is not very hard. It's doable, but I'm not going to explain it during class because it's really a little bit beyond. Okay, not a little bit, but it's kind of way beyond the scope of assembly language programming. So for people who are willing to kind of explore all of these options, you're more than welcome. I will make a separate video to explain how to do that. Okay, but for people who absolutely do not want to go through all that hassle, all you have to do is to learn how to run Logisim on the command line like this using your operating system, which I think is not terribly difficult. You just have to learn how to specify a file path in your operating system. And I think to someone who is inspired to become a computer science person, that really should not be a big hurdle. All right, so I'm going to take row at this point so that you guys can take a small break from all this complicated stuff. So the row taking test is sort of set up, except I have not released it. So I'm going to click on this, show you the answer, give you 5 minutes, and then we'll quote unquote collect it. Alright, so here's the question, and the answer to the question is stack. So I'm going to type it in the text channel. Stack is the word for today's row taking. Now I have to go back and release it. It's 25. I'll give you guys up to 31, 631. So we'll go to do July 13th, 6:31 p.m. All right, save and publish. There we go. All right, so go ahead and get to the row taking activity, type in the word stack all lowercase, or just copy and paste from Discord. And I'm going to keep an eye on how people are doing so I can decide when to continue with the lecture. All right, I see most people have it done already. And I'm going to refresh the page one more time. All right, no change since last time. All right, so I'm going to continue with the lecture at this point. All right, so, right. Let's do, okay, first of all, are there any questions about the concept of the program that I just wrote? Let me bring up the source code, and you guys can ask questions. The left-hand side, I don't think there should be any questions because that is really simple in C++. The right-hand side, not so much because it involves the use of the stack to store the return address and so on. All right, I am not seeing any questions. So without any questions, let's go for something that is a little bit more difficult. Okay, and specifically, we are going to do a recursive subroutine. And recursion is actually not any more difficult than non-recursion, because recursion is simply referring to the case when a subroutine is indirectly or directly calling itself. And in this class, we are going to deal with recursive algorithms, except that I will always give you the source code, and your only job is to translate the source code into assembly code. But it doesn't hurt that you understand how subroutine works and also how recursion works. So for this particular example, I am going to use a global variable. Personally, if I could avoid the use of global variable, I would, except in this case, the main point is not about the use of global variables or lack thereof. The point is about recursion. So I'm going to use a global variable called x here. And x is going to be initialized in main, and we'll make it, I don't know, 3. And f is only going to be called once. And inside f, we are going to use a conditional statement. And we say if x is greater than 0, we will do something recursive. Otherwise, we do absolutely nothing. We're done. So in the recursive case, we'll say the first thing we do is we decrement x, we decrease the value of x, and then we call f again. So this is a very simple case of a recursive algorithm that does absolutely nothing other than counting x down to 0 in a recursive way. But other than that, it doesn't serve any purpose. Okay, so the only purpose of this code is really just to illustrate how to use a global variable in this case, and also how to use a conditional statement and how to do a recursive call. So now we go back to the assembly code, and we will make some changes. So the first change is we have to reserve that byte for x. So the way we reserve a byte for a global variable in assembly code is something like this. Okay, I could have just specified byte 3 to make it initialize to 3, but I'm not going to do that. Okay, because I want to show you guys how to utilize a global variable in the context of assembly code. So what byte 0 is doing on line 6 is it is reserving a byte, and in this case it is not an opcode, it is just a byte in RAM that is right after the JMPI instruction and right before the LD instruction here. That byte is initialized to a content of 0 because we're going to initialize it in main. So here's main. We still have to do the other stuff, but the first thing to do is to initialize x to a value of 3. So we know the only instruction we can use to store content into RAM is a ST instruction. So we know that we're going to need an ST instruction like this eventually. And we also know that in an ST instruction, the inside the parentheses has to be a register, and then after the comma also has to be a register. So we can store the value of a register to a location in RAM that is pointed to by a register. They can be the same register. It's not very usual that you would use the same register for both purposes, but it can be the case. It can happen. In this case, we're going to stick with register A and register B here. Now, why did I pick register A for the register supplying the value, and why did I pick register B supplying the address of RAM, that is of the where in RAM the byte is going to be changed? That's just arbitrary. That is completely arbitrary. Anything other than register D is going to be okay. But since now we have determined that register A is the value that we are going to store, and register B is pointing to the location where the byte is going to be updated, we just have to do something like this. Okay, LDIA with 3 because 3 is the value that we want to store, and LDIB with the label of the global variable. And that's all we need to do. This is going to initialize the global variable x to 3. Line 15 to 17 will accomplish x equals 3. Alright, with that done, we just have one call this time because the second call is no longer here, so we're going to delete all that code. So now the tricky part is, what are we going to do in function f? Well, in function f, we still have to return eventually, so line 9, 10, and 11, they still have to be here, so I'm not going to mess around with those. So first of all, I need to implement the conditional statement, and the conditional statement needs to know whether x is greater than 0 or not. And we also know the type of x, not from the assembly code, but in the C code. In the C code, we can see x is an unsigned 8-bit integer. So you can either go through the whole thing of doing the compare, or you can use the trick that we have done already, which is using the AND operation. So we have to first get the value of global variable x into a register. That's not too difficult because we just have to do the reverse of a ST instruction because we want to load the content at that location into a register. So we do a LDI. Okay, this time I'm going to use register A to be x. So at this point, A is the address of global variable x, and then we just do a LDAA. So we're using register A as the address in RAM where we're going to retrieve a byte, but once we retrieve that byte, we are going to use that byte to overwrite register A. So register A now has the value of global variable x. So this is something that you might want to write down. Once I give you a copy of this code, is you can kind of jot down some comment, and so that you can know that after line 9, register A has the address of the global variable x, and after line 10, A has the value of the global variable x. So continuing with this code, all right. So now that we have the value of x in register A, I'm going to use AND AA to basically just get the value of A through the ALU so that we can use it to affect the flags. The one flag that is going to be useful here is the Z flag, because if I say x is greater than 0 and x is known to be an unsigned integer, it simply means x is not 0. That's all it says, right? So if it is 0, we want to go to the else case, and there's really no else case here, but that's okay. We'll just go ahead and pretend there's one, and then we define the label corresponding to it. And obviously it's not going to do a single thing, but we're going to say, there's an AND if here right after the else. So if I did have any code in the else case here, it would be between f_else and f_and if. This is all coming from the module that talks about how to compile code, how to change C control structure into assembly code. So we covered this already, especially if you read the entire module by yourself, because there's an example at the end of that particular module that talks about how to do this step by step. So I'm counting on you to have read that. So this is JMPI around the else case, which is not really needed in this case, but since I did use the if then else structure here, I really should put a JMPI to f and if here. Even though it doesn't serve any actual purpose, but at the same time it is not wrong. And in the future, if I really want to put something into the else case here, I now have a space to do it. So inside the then branch of the conditional statement, I need to decrement x. So I'm going to do a little shortcut because I know that, okay, so I'm going to change the program a little bit, because now I don't want to use register A to store both the address of x and also the value of x. So I'm going to use register B to store the address of x, and then use register A to store the value of x. So at this point, okay, I know that B has the address of x, and I also know that A has the value of x. So given these two are in those two specific registers, decrementing is going to be easy because I just have to decrement A because A has the value of x. I have to decrease that by 1, and then I have to store it back, right? Because I have to store that back to update the global variable x. But since b still has the address of x, I just have to do stba, and that will update x so that it is now decremented. So this is going to accomplish the minus minus x. Now I have to call f again. So when you're calling f from inside f, guess what? It makes absolutely no difference whatsoever, compared to how we did it in main. It's just that the label they have to be different. Okay, so we follow exactly the same steps. Okay, we first define a point where it is going to return to, and let's call that recursive call returns here. Okay, that's a pretty long label name, but it's okay, it will work. And then now we put it into register A, because at this point register A does not have, we don't need to retain the value of x in register A anymore. We are done with the minus minus x statement. So we can reuse register A. So it is recursive call returns here. And then we do the usual thing, decrement D to reserve a byte on the stack. STDA, right? This is how we push a value onto the stack. And then we JMPI to the subroutine that we are calling, which coincidentally is the same subroutine that we are in, but it doesn't change a thing about how we make the call. So I hope this actually helps to demystify how recursive call is done in CISP360. And for those of you who have taken 400, 430, and there will be a lot of recursive subroutines in 430. But this is it, okay? A recursive call is not any different compared to a regular call. It's just the placement of the call is in the subroutine that you are calling, either directly or indirectly. That's it, okay? All the magic has to do with the stack, okay? So I think this program is done, okay? I'm just double checking a little bit here. Yeah, I think it's done. Line 24 is not a label. Right, because it is highlighted, because I forgot to put a colon after that. Thank you. There we go. This is why I made the syntax highlighter, so that you guys can look at the screen and go like, that color doesn't look right, and then remind me that something is wrong with the program. I'm just kidding. All right, there we go. All right, so we're going to use the auto magic script to do this. Okay, so the auto magic script is, let's see, it's in the folder, push directory to where the script is located, which is documents, CISP310, river spider. And we'll just do a submit /temp call.ttpasm. Oop, ttpasm. There we go. And see whether it works. All right. So the script thinks it's done. Let's go back to the assembler and check. All right. So the analysis tab was just updating itself. Now it's fully updated. All right. So now the question is, how can we tell whether the program worked or not? Okay. I'll tell you a few quick tricks. Okay. A few quick tricks to tell whether your program worked correctly or not. First thing is to go to all the way to the end of the trace and see whether the last instruction is the designated halt instruction that should stop main. And to get to that, we go to summary, and it tells us that we only have 102 lines of trace. Okay. Let's find out. Doesn't seem right to me, but I could be wrong. So we'll go to analysis and then go to A102. So click on this icon and just type it, and type A102 in this case. And now we are at the end Or did I mistype something? Nope, should be right. Okay, let me check it one more time. Alright, this is 102, and when we get back to analysis, this is 102. Not quite sure why there's a it's off by one row. Okay, basically it's off by one row because I think 24 is where the halt instruction is located. Alright, so to double check that, we have to go to the Assemble tab and check out where the halt instruction is. So the halt instruction is at location 24, so somehow it's off by one line. But the analysis is done correctly. We did end up with register D, the stack pointer being 0, 0. So it looks good. Okay, looks good so far. So the second thing now we need to do is to look at the recursive call and ask ourselves how many times should we end up at the label F. Okay, so for that, I think it is helpful to look at the C code and the assembly code. So we'll go ahead and take a look at that. Where's my, there we go. All right. And by the way, the C code does work. Okay, you can actually compile the C code to find out how many times we should end up at the label F. So there's one call from main, so that's one, right? Inside the recursive call, the first time we get into F, X has a value of 3, so it's going to recursively call again. So the second, after we decrement, so the second time we call F, X has a value of 2, and then we end up here again, and X has a value of 2, but by the time we perform the third call, X has a value of 1, and then it will get back to F again. The value of 1 is still greater than 0. We decrement 1 down to 0, and we perform the last call. So we should have 4 invocations of F that are simultaneous. Okay, so we are basically stacking up 4 calls to F in this case. So that means in the assembly code, I should be able to see in column A, in the analysis tab, I should see 4 times, okay, that column A has the value of label F. So let's check whether that is the case. I can actually come back here in just a little bit to show you, what you can do in GDB to do the analysis of the C code, so that you can understand the C code behavior before you debug the assembly code. All right. So first thing first, we go to the Assemble tab, find out where the label F is located. So label F is right here. It is at location 6. So now we go to the Analysis tab, and we highlight column A, and then we go to Edit, and then we say Find and Replace, and we want to locate 06 exactly. So we want to find out how many times we got to location 06. So we click Find. So this is the first 1, 2, 3, 4, and back to the first one. So we counted exactly 4 of those cases. Now, if you're good with your spreadsheet, you can also use count if. That's also a really nice spreadsheet formula to use, but I would probably not use it within this particular sheet. You can create a new sheet to use your custom function to do some custom processing, but find and replace is not too bad. I mean, it seems to work. All right, so the behavior of the assembly code seems to resemble the C code, or at least that's what TAC is claiming. So now the question is, how do we know that the C code is supposed to call F also exactly 4 times? So to understand that part, we have to use GDB. So I'm going to compile the C code by hand, gcc-g to include debug information, -o to specify the executable's name, which is call, and then you supply the source code, which is just call.c in this case, and then GDB the executable's name. And by the way, all of this can also be done in online GDB or code blocks or VS Code or whatever IDE you used before when you took your C or C++ class. So now we're in GDB, and GDB is kind of nice because you can just do a BF, which is not best friend. It is break at function f. So this will insert a breakpoint at the very beginning of function f. There we go, and then we run the code. So R for running. So this is the first time we got to F, and then you can see continue to get to the second one, and C again to the third one, and C one more time to the fourth one. So now the question is, but we don't know whether we return from the first one before we call the second time, and then we return again before we call the third time. So now I'm going to show you a really, really cool command. It is called, of course, I cannot remember the backtrace. That's it, BT. So backtrace, or just BT, is going to show you the invocations, how they stack up on top of each other. This is called frame number 0. This is called frame number 1, and so on. The frame 0 is always referring to quote unquote the current frame, which is where the program has stopped at this point. But if you want to ask, how did we get to function f on line 7? The answer is we called f from line 10, which is also in function f. But if your question is, how did we end up on line 10 in function f then the answer to that is we got to line 10 of function f from line 10 of function f. Then you're going to ask, how did we end up there? The answer is, once again, we ended up there because we called f from line 10 in function f. And if you ask one more time, how did we end up there? Then the answer is going to be, we called f the first time on line 20 in main. So this is what you can do in GDB. In online GDB, I think you can just type the commands in the little command window inside the interface. In the other IDEs with code blocks, you can also directly enter commands like this in GDB. In VS Code, I am not sure, okay, because I do not use VS Code, so I cannot tell you how to get to something like BT in VS Code. It has to be there because this is a very crucial feature of a debugger, especially when you're dealing with a lot of call levels and potentially recursive subroutines. So how are we doing? We are running out of time. I will release the lab today because now you have the tools to get it done. Okay, you just have to, you might need to refer back to the recording, just so that you can know exactly how to do that if you have not been taking notes. And that's okay, because that's the whole idea of me recording the lecture, is so that you can go back to it. The first few questions does not rely on being able to use the trace analyzer, so that gives YouTube time to transcode the video. So by the time you need to go back to the video, it should be done already. All right. Do we have any questions before I stop the screen share and go away for 10 minutes and then come back in just after eating a little bit of food? How is Discord working today? Is it satisfactory or is it still kind of choppy? All right. Well, I mean, as well as it could be, because my computer is really loaded. I mean, it's running out of juice. It's just a laptop computer, by the way. All right. All right. So the practice exam was already released yesterday, so you can go back to the text channel from yesterday. I already attached the practice exam. So tomorrow I'm going to go over the practice exam. The practice exam will go over everything. Let me show you what the scope is going to be. So the practice exam is going to include everything up to, but excluding assembly language programming. So it will include everything up to simple branching and code analysis in terms of the lab. So you're going to have to understand the architecture of the processor. It's open book, open notes. Okay, you can't open up Logisim and bring up processor 0004 during the exam. So that's not a problem. It's just that if you already know how the components relate to each other and how the ROM controls the various components, that's what I'm testing. So there we go. So that should answer Barak's question of when I'm going to practice to answer the practice test for the second exam. It's already released from yesterday. So if you go back to the text channel of yesterday, there's already a copy of that test. And in the HTML file, I think there's a link that is missing, and a few people found, the actual link to those bitmaps. Yep. Okay. Cool. All right. That's cool. All right. So let me release the lab for tonight, and that is called stack operations. Okay. Not very surprisingly. And I'm just looking at the time. I'll give you guys the 5 minutes back. And let me quickly go over the questions, because in one of the tests I made one question worth 0 points. I just want to make sure it's not this particular one. Okay, it's not a question. The last one is not a question, so it has no points, no point value associated with it. All right. All right, so the passcode of this is called LIFO. I'm going to type it in the text channel. So the access code to the lab is LIFO, all lowercase, last in, first out, which is another way to describe a stack. And it's going to do today, July 13th, at 8:25 p.m. Here we go. Save and publish. And now you can get started with the lab. All right, cool. I'm just going to double check in the text channel for the next 10 seconds to see if I have any more questions to answer before I go offline. Well, I shouldn't say go offline. I just go into text mode instead of synchronous mode. Okay, we got one question coming, so that's good. I'm going to wait for that question before I go offline. Doesn't look like the question is coming in the text channel, so I'm going to stop. Alright, so I will see you guys in the text channel in about 10 minutes.